So we're going to continue and start doing arithmetic with sets in this last lecture. So we'll be able to understand set operations and the connections with logic. We'll be able to look at properties of set and logic operations and Venn diagrams to sort and reason with data. So let's consider I have two different sets. The first set is going to be college graduates, and the second one is going to be earns at least $40,000 a year. So suppose we want to take a survey and we're going to mail out questionnaires to individuals in the city who are college graduates who also earn at least $40,000. So these individuals that get the questionnaire would be common to both set C and S. So the intersection of C and S is who I'm trying to reach. I'm not trying to reach college graduates that make less than $40,000 over here. I'm not trying to reach students that earn less than 40,000 over here. So the intersection would be that shaded region. The intersection of two sets is written as A intersection B, and the set of all elements in common to both A and B would be written as the intersection of A and B. So when I see this upside down U, it means everything in both sets. That's all it means. So if I have this set and B, everything in both sets would be here. Sorry, not everything. It's what's in both. It's the intersection. So 3 and 4 belong to both. Here, what belongs to both? Well, B has no 0, B has no 2, B has no 4, B has no 6. So there's nothing in common, so they're disjoint. Here, A intersects B. It looks like every value in A is contained in B, so I could just call it A. So if I want to make this into a word problem, if we know that 4,800 people have college degrees and 5,400 people earn at least 40,000 and 1,200 meet both criteria, then this is what that's going to look like as an image. So 1,200 meet both, then I have my other number here and my other number here where they don't intersect. So let's look at set unions. So set unions is what I had mistakenly said before. The union is when you're adding all elements of both sets. So that's written as the upside right U. So this is every element in A, every element in B. So or it's also said A or B. So anybody in A or anybody in B can be a part of the set. So here I'm just combining. Now notice if a number occurs twice, I don't write it twice. That's really important. I only write it once. So if I want to know the complement of A relative to B is B take away A. So I want to take a set of elements in B that are not in A. So it's not read as B minus A necessarily. It's not an arithmetic operation. I'm taking the set of all elements in B that are not in A. So I'm basically subtracting out any elements that are found in A. And this is the set of elements in B, but I'm taking out everything in A, which means A is completely unshaded. So here I have elements of A and B, and I want to take away any elements of elements of B out of A. And when I do that, I take away D, E, and F, so it's empty. Then I want to take away elements of A that are in B, which leaves me with A, B, C. And I can keep doing that process of and you can almost cross out. So if I'm looking at B and I want to take away the things in A, D, E, F gets crossed out, I'm left with A, B, C. So I have cumulative properties, meaning that they can switch sides. It doesn't matter if it's A first or B first, we're going to arrive at the same answer. So set operations are commutative when I'm looking at OR statements. The associative property applies to set operations by moving the parentheses to do things in a different order, and it will not change the final answer. The distributive property is also true. So I could distribute A with my intersection to B and to C, which forms two sets of parentheses, just like you would do the distributive property with 3 times x plus 1. So in set notation, if I'm trying to describe the shaded portions, I would say that this is the grouping of A and B, and I'm taking away where A intersects B. So I'm taking A and B together, all shaded in, and I'm subtracting out where A intersects with B. And then in the second one, I'm taking A, B, and C, but I'm taking out those A, B, and C where they're not intersecting. So I can describe it solely as where they intersect. So where A and B is going to intersect with my B and C, or where B is going to intersect A and C. So here are some additional examples with images. These can be a bit tricky to get used to. So now I want to suppose I have a new situation where M is a set of all students taking math. E is the set of all students taking English, so M and E. And then the intersection B would be people in both classes. So A would be just students in math, C would be students in English, and B would be students who are there. Now it's important to note that A does not count students that are in math and English together. Same thing with C. C doesn't count those that are in there both. And region D contains all students that are taking neither course. And here the universal set is just students. So if I'm looking at a survey that investigates the high school backgrounds of 110 freshmen, I have the following breakdown. If I want to answer these questions based on that breakdown, using a model is going to be the easiest way. So I'm using my model to have 14 here in P physics. I have 36 taking biology by itself, and I have 35 taking math by themselves. Now these 5 people here are taking physics, biology, and math because it's intersecting both. These 3 here are taking biology and math, and these 5 are taking physics and math. So there's some overlap here. So because there's a total of 10 students who took physics and mathematics, comes from adding these two 5s together, and 5 of those also took biology. If I take those 10 and subtract 5 out, students who took physics and math but not biology, and then because I have 8 students that took biology, so 5 plus 3 is 8, and 5 took all 3 subjects, I would take that 8 minus 5, and I would have my 3 biology kids chilling that took biology and math. So to find the number of students who took biology, but neither physics nor mathematics, that would be the 45 that I had. And then I'm going to look at the number of those that are in the distinct regions that include biology. So I have 1, 5, and 3, or 9 total, because you have this one guy up here. Because 45 minus 9 equals 36, we know that 36 students took biology, but not physics or mathematics. So the 36 on the outside doesn't encompass the whole circle. It just encompasses the region that's there. So the number of students then who took physics, biology, or mathematics would be the sum of everybody inside of the set, not including those 11 students that took none of them. One way to produce a set from 2 different sets is by forming pairs of elements of one set with the elements of another in a specific way. So let's suppose that a person has 3 pairs of pants and 2 shirts. According to the fundamental counting principle, I have 3 pairs of pants, 2 shirts, 3 times 2 is 6, which gives us the total number of outfit options. Or I could get this nice Cartesian image where I'm plotting out my options. So blue shirt, red pants, white shirt, red pants, and so on. Because the first component in each pair represents the pants, so blue pants, red shirt, white pants, red shirt, green pants, red shirt, blue and blue, white pants, blue shirt, green pants, blue shirt. So I'm basically using ordered pairs to represent this instead of in a tree, but it still gives us the total options. I have 3 pairs of pants that are options, two shirts that are options, and I'm writing them as ordered pairs instead of as a tree. My ordered pairs are equal if and only if the first components are equal and the second components are equal. That should make sense. 2 comma 1 is only equal to 2 comma 1. So when I'm looking at these ordered pairs, I have groupings here that A cross B should never be read as A times B. So this is not multiplication. This is called cross. So that would be the set of all ordered pairs such that the first component is an element of A and the second component is an element of B. So we're taking two distinct sets and making ordered pairs. So if I want A cross B, A and 1, A and 2, A and 3, B and 1, B and 2, B and 3. So you get a lot more ordered pairs. You're going to determine your ordered pairs by using the principle of counting. Then if I want B cross A, my B elements have to come first in the ordered pair. And if I have A cross A, my A elements come first, and I'm crossing A with itself. It is possible to form a Cartesian product involving the null and the empty set. So to do this, I could have A as 1, 2, but because there are no elements in the null set, there are no ordered pairs. So this set is also empty. So when we're forming the cross there with the Cartesian and we're looking at the null or the empty set, it's just empty because I don't have two things to make it with.